Okay, man. Right. Okay, thank you very much. And good evening to all of you. We'll start within few seconds. Please wait. So yesterday I explained about strain energy. So here today I'm going to explain all the cases belongs to strain energy. I told you yesterday very clearly there are different types of cases comes under strain energy. How to find the strain energy formula in different loading conditions. Yeah, right. So today our topic is strain energy. So please careful about this strain energy. I have already told you yesterday that the topic is over now. That is strain energy, strain energy, and a gradually apply load or static load or axial load. That is gradually apply load, suddenly apply load. That is there are different types of cases are there. Strain energy under gradually apply load. Apply load that is we know that is sigma square is sigma stage u is equal to sigma square divided by 2 times of E into volume. This is the formula for stage and a gradual apply load. So this is case number one. I told you yesterday very clearly. And the second case is nothing but strain energy and suddenly apply load. That is suddenly apply load. In case of suddenly applied load, we are not taking the load or is not an average load. So we are taking the direct load which is applied directly or suddenly on the component. So U is equal to we are taking sigma square, remove the 2 here, sigma square by E into how much volume. And the third one that is we are going to discuss now here, this is stage under impact load. So stage under impact load. Now we are going to discuss here now. As already yesterday, I have given some explanation about this case, and today I'm going to give the complete analysis of this case. After that, I'll give remaining cases under torsion, under shear, under bending. What is the value of shear stress? Okay, so listen carefully. What is the formula? We can get it. So in case of strain energy, when the component is subjected to impact load here, impact load here. So this is the diagram. This is the diagram. I'm going to give it to you. So this is the bar which is fixed at one end, which is hang vertically. So this is the bar. At the free end of the bar, we are connecting a negligible weight here. So that is negligible weight. So here we are taking load, that is nothing but P external load. So which is sliding on this bar, which is sliding on this bar, which is at a height of h from the bottom of the bar. This is the height of h. Now it can slides in upward direction and downward direction. So if you release this weight, if you release this weight here, and it slides down vertically and goes to impact this negligible weight, at the same time the bar will deform like this. The bar will deform like this. So what is the deformation here now? The deformation is equal to how much? Delta L. Deformation is nothing but delta L, or we can take delta L or delta. In some textbooks they are written as delta also. I got the point or not? Right. So here, I'm going to write as here, when this load is released suddenly, then it travels with an acceleration and goes to impact this lower portion, and this bar undergoes some extension. So here I want to find it, what is the strain energy in this bar here? What is the strain energy here? So I'm writing here strain energy is always equal to work done. I have already told you strain is always equal to energy stored in the material. So when the material is deformed from this point to this point, then automatically some energy is stored within the material. If you release this weight here, then automatically this material comes to original position. Such type of material is named as elastic material, and it follows Hooke's law. It follows Hooke's law. Or you got my point or not? It follows Hooke's law, right? Now here, what is the strain energy here? Strain energy is equal to work energy. Work is equal to how much? Force into displacement. Force into displacement, right? So here, what is the force here? So force is nothing but P. Force is nothing but P. Displacement is nothing but this is the total displacement H plus delta L. I can write it. That is the total displacement of this one. So here, if you release this weight here, which type of energy contained by this weight here? This weight contains potential energy. The weight having potential energy. So when this weight goes to impact this bottom portion, so it lost its potential energy and converts to strain energy. So are you got my point or not? So if you release this weight here, then which type of energy it contains here now? It is having potential energy. It is having potential energy. So when it goes to impact this lower weight, and that means this weight lost its potential energy. So I'm writing here potential energy is nothing but m into g into h. Or you got my point or not? So that the loss of potential energy must be converted into strain energy in this material, in this portion. So this is the portion which is having strain energy. So I am writing here generally, this is the strain energy force into displacement. Generally, we can write it here. Loss of potential energy, loss of potential energy is equal to strain energy stored in body. Strain energy stored in the material. Strain energy stored in the material. Are you got my point or not? Right? Are you got it? Right. So I'm writing here, we have here strategy is nothing but generally so after impact it is uh, we can write it here. from this point after impact, it is deformed from this point along with the negligible weight. So I'm writing here, state the general formula is sigma square by 2 times of E into volume. E into how much? Volume. So that is the formula for strain energy from this point. Then it is equal to, so that is the work energy. Work energy is nothing but P into H plus delta L. So that is the formula of strain energy. Or you got the point or not? So here sigma square divided by 2E into volume is nothing but area into L is equal to PH plus delta L. And I'm writing PL plus delta L is nothing but PL by how much? AE according to Uppsala. According to which one? Uppsala. Or you got my point or not? According to which one? Uppsala. Then I'm writing here sigma square by, so here I'm writing again, that is sigma square by 2E into area into length is equal to area into length is equal to pH plus pH plus, we are writing simply so P into, that is P into, can write here into pH. So here is into P also we are getting. So P into PL by AE we are. So this is the equation we are getting here. Now I am writing like this also. See this one. I am writing like this also. So here I am writing sigma square divided by 2E into volume. Volume is nothing but area into length is equal to, between these two, what is the common term here? P is the common term, so I'm going to take the P is common. Then I'm writing here H plus P into L divided by E. I'm writing here. I got my point here. I got my point or not? Right? So then I'm writing here P square divided by, that is nothing but stress. Sorry. Okay. Right? I can write it like this. That is sigma square by 2E into area into L is equal to, so P into P by A into L by E plus P into H. So this is nothing but sigma. So I am writing here P into sigma into L by E plus PH plus pH. I got my point or not? So here I am writing here. So take this one. So I'm going to divide on both sides by, I'm going to multiply it on both sides by, this is nothing but sigma square by 2E into area into length. So multiply on both sides by 2E by AL. 2E by AL. So then how much value you get here? Here I am getting here. So generally I am getting here sigma square divided by 2E into AL. So divided by 2E into 2E into AL. So is equal to P into that is sigma L by E into 2E divided by AL plus PH into AL by 2E. Sorry, 2E by AL. 2E by AL. So then here this 2E this is cancelled. Then sigma square is equal to, so here I am writing here E get cancelled, LL get cancelled. Then here I am writing sigma into 2 times of P divided by A. 2 times of P divided by A plus what the value 2 into P into H into E divided by A into L. A into L. So this is the equation we got it. Then again I'm writing here sigma square minus sigma into 2P by A plus that is 2 into P into H into E divided by AL must be is equal to 0. So this is in the form of a quadratic equation. If it is a quadratic equation, we are going to find the solution of the quadratic equation. I got the point or not? What is the solution here? Solution is nothing but I'm going to write it here. So take care about that things. So that is I'm going to find sigma. So we know that sigma is equal to minus b plus or minus square root of b square minus 4ac by 2a. So this is the formula for roots. If the roots are not coming to this equation, then we can follow that formula. Then we can write here a is equal to 1, b is equal to minus 2p by a, and c is equal to minus 2phe divided by al. So these are the values of a, b, c. Then I'm going to substitute those values in this equation. So this equation, so sigma is equal to minus p, that is minus 2p by a plus positive plus or minus square root of 2 into p by a whole square minus 4 into 1 into minus into minus positive 2phe divided by a into L in that value. Then I am taking the divided by 2a divided by 2 into 1. Then sigma is equal to 2 times of p by a plus or minus square root of. Then we can write here 2 is the common. 2 is the common. Then I am writing here p by a whole square plus here is also 2 is the common. So that is 4 square. 2 is the common. 4 square. 2 square is also there. Then we are writing here 2phe divided by a into L. Or got the point or not? Divided by how much? 2. 2 to all are cancel. Then I am getting the equation here. Then I am writing the equation here. Or you got the point or not? So sigma is equal to so I am taking so p by a is common. P by a is common. So here I am going to multiplied by a and divided by p. Right. See this one. So first of all, I'm going to take the p is a common term. P by a plus or minus square root of. I'm writing p by a plus whole square plus 2 into p into h into e divided by a into L. So here I'm going to get it here. So p by a whole square multiplied by p here and divided by p here. So multiplied by p here, divided by p here, multiplied by a here, divided by a here. Then all are cancelled. Then automatically we will get this equation like this. See this one? Sigma is equal to p by a plus or minus square root of p by a whole square plus. So we can write here 2 into so p square by a square by a square. P square is over a square is over. That is h into e into a divided by pl. Divided by how much? Pl. Then I am taking the p by a is also common here. So p by a is common. So we are getting 1 plus or minus square root of 1 plus 2 into h into e into a divided by pl. So this is the formula we are getting for sigma. We are getting for sigma. Or get the point or not? Or you got it? So here, another one here, P get cancelled. So here is P square is common, A square is so P into L we are getting here. I got the point? All right. Right. So here I did a mistake, small mistake. So correct that. That is, we are having sigma is equal to P by A plus or minus square root of P by A whole square plus 2 into P into H into E, 2 into P into H into E divided by AL. So that is the value of sigma. I got the point or not? So here, so when delta L is very, very small, when delta L is very, very small, for example, if delta L is very, very small, then what happened here? This one is what happened here. That is pH is equal to how much? Generally, we are writing so sigma square by 2E into A into L is equal to P into so H plus delta L. So here we are getting delta L is which one is delta L is very very small. Then we are getting sigma square by 2E into AL is equal to pH. Then we are finding the p value. Automatically we can get it. So that is the value of p. I got my point or not? Right. So this is the formula, we can remember it. So to find the what is the maximum stress in the material under impact load. So this is the case of the strain under impact load. So please take care about that one. So right. Right. And three cases covered. So stage under gradually apply load, stage under suddenly apply load, stage under impact load. Three cases over. So in this case, we are having this formula. So listen carefully. So we are getting the formula sigma is equal to P by A plus or minus we are getting that is P square by A square plus 2 into P into H into E divided by area and L. When delta L is very very small, then we are getting pH is equal to P value stress is equal to how much square root of 2 into P into E into 2 into P into E into A E in P into sorry 2 into P into H into E divided by area into L. So that is the value of sigma. Right. Now next one I'm going to explain to you stage under pure torsion. strain energy under pure torsion. Strain energy under pure torsion. So what I am saying here, so this is the shock which is in the form of circular. If you apply the force at this point and at this point, both are having same magnitude and the directions are opposite to each other. This is said to be radius. Then what is the torque on this one now? So here, if you take this is the point A before application of this force P or AF, AF. So before application of this force, twisting force, I'm taking the point A. After application of this force, this point will displace from this point to this point. This is nothing but angular displacement theta or displacement of the point A to A dash here. A to A dash here. So here I am writing what is the strain energy here. So strain energy means when this point is displaced from this point to this point, automatically the material is said to be under strain here. Under strain here due to the twisting of the material. So here I am writing here strain energy is equal to strain energy U is equal to work energy. Work energy. What is the formula for work energy here? Work is nothing but force here into displacement here. What is the force here? Strain energy is equal to force is nothing but torque. So torque we are going to apply it on this material. And displacement is nothing but theta. But torque we are always taking the average torque here. We are taking always average torque here. So here torque I'm writing half into T into theta. Half into T into theta. But we know the torque equation. So T by J is equal to tau by R is equal to G theta by L. That is the torsion equation. All of you know very well. All of you know very well. Have you got my point? Or you got my point or not? So from this equation, I am writing here is T is equal to tau into J by R. Tau into J by R. Tau into J by R. Okay. So what is J value? So I'm going to write it again here. So listen carefully. U is equal to half into T is nothing but tau into J by R into theta. What is theta? So so we can write like this also. Okay, no problem. Otherwise, we can write like this also. So half into T into theta. From this equation, theta is also is equal to what is the formula here? Tell me theta is equal to how much? T into L divided by J into G. Then I am writing here half into T into theta is nothing but T into L divided by J into G. That is the value of theta. Then I am writing U is equal to half into T square into L divided by J into G value. So now I am writing here half into what is the T square value? T is nothing but, so here I am writing tau into J by R whole square divided by J into G value. So that is the value of T. Then I am writing the formula. Then I am writing it. So half into 1 by J into G into tau square into J square divided by R square. So here one J is get cancelled. Then what is the formula we can get it here? So I am writing here U is equal to half into U is equal to half into U is equal to half into what is the value? We are writing tau square divided by G into J square divided by R square. I got my point. So I am writing here half into tau square divided by g into what is the j value here? J value for circular shaft. That is, I am writing here pi by 32 times of d power 4. I got my point or not? J value for solid circular shaft. Then I am writing here pi by 32 times of j value. Zp value we can write it also. That is pi by 32 times into, sorry, j only we are having, into d power 4 divided by r square. R square is nothing but d by 2 whole square. R square is nothing but d by 2 whole square. Now I am writing here, u is equal to, now I'm writing here u is equal to half into half into tau square by g into, so here 4 is here, we can get here 8 times 1 d square is cancelled. Here is we are getting d square. So I am writing that value 1 by 2 into pi by 4 into d square. So what is this one here? What is this one here? Into L is also there here. Into L is also there here. Into L is also there. Into L is also there. So here into L. Then here I am writing 1 into 2 is nothing but 1 by 4 g times tau square into, this is area into L, that is pi by 4 into d square into L. This value belongs to volume. So I'm writing strain energy in pure torsion is equal to tau square divided by 4 times of g into how much? So this is the formula for strain energy under pure torsion. Under pure torsion. Very simply, we can remember this formula. This is the case of pure torsion. So as same as we can find the formula of that is pure shear also. That is how much we get, I'll give it to you. What is the value of pure shear? After that, I'll give the what is the stage and bending also. So here I am writing the four formulas. So strain energy under gradually applied load is nothing but sigma square by 2e into volume. And next one is strain energy under suddenly applied load is nothing but sigma square by e into volume. And gradually applied load, that is impact load is nothing but that is 2 times of that energy now. That is a formula is nothing but strength is equal to work here. Work is nothing but P into how much? So H plus delta L. That is equal to strain energy. Then we are getting the formula of impact load here. And here is nothing but strain energy and the torsion is equal to tau square divided by 4 times of G into how much? Volume. So 4 cases is that is what is the strain energy in different cases. And next one I'm going to give it to you strain energy under pure shear. Under pure shear, how much you get? That is simply you can write tau square divided by 2g into how much volume we can write it. So I'll give it to you simple explanation how to calculate the value here. Under pure shear, for the case of pure shear, what is the value of strain energy? So look at this. I'm taking this component which is fixed at one end, other end is free, which is fixed at one end, other end is free. So on the other end, I am going to apply some force which is parallel to the surface, and the surface also gives some force. Both are having same magnitude, but directions are opposite, so that the material rotate the clockwise direction or in anti-clockwise direction if you apply the force in reverse direction. So the material will deform like this. So this is the height of this element. This is the height of this element. Are you get my point or not? Or you get my point or not? So here I want to find what is the strain energy. So if you apply the force parallel to the surface, it will deform like this. Automatically we can get the strain value also. This value is nothing but phi. It is named as shear strain also. I got my point or not? So here I want to write. So what is the work here? So if you apply the force here, if you apply the force here, then what about the um, work here? How much work done by the force here? So if you apply the equal and opposite force, this member will rotate either clockwise or anti-clockwise direction. That is very clear to all of you. So that is nothing but due to these two equal and opposite force, there must be a couple here. There must be a couple here. So I am writing here strain energy U is equal to so coupled due to the force, coupled due to force into displacement. That is nothing but strain here. That is couple is nothing but how much. What is the couple here? Force into distance here. That is F into H. And here is displacement is nothing but how much is angular displacement here, that is nothing but phi. So I am writing this value is nothing but phi here. So couple due to force into phi here. So here I am writing here strain energy is equal to strain energy is equal to, or otherwise we can write work is equal to force into displacement. Force is nothing but shear stress into area, and displacement is nothing but phi. We can write it. Then we can write here force is nothing but always average force. We can write it. Then we can take this phi is equal to some value. Then we can write it very easily. So here couple is equal to how much? Force into this perpendicular distance. So here is force into perpendicular distance h into phi. So here I am taking force is in average force. That is average shear force. So strain is equal to half into what is the force here? That is shear force. The shear stress is equal to force by area. That implies force is equal to shear stress into area. So I'm writing shear stress into area into H into how much? Phi value. So strain energy is equal to how much? Half into stress into this one is nothing but volume. So phi into how much? We can write volume. So directly we can write like this also. Strain is equal to half into stress into. So this is shear strain. We know that according to Hooke's law, when the component is subject to under pure shear, shear stress is directly proportional to shear strain. It is if we remove the proportionality constant, we can put a constant. That constant is nothing but G. So what is phi value? Phi value is equal to tau by G. Then I am writing here tau by G into volume. Then what is the formula we get? That is 1 by 2 times of G into tau square into volume. So this is the formula for strain energy under pure shear. Under pure shear. So this is the way of calculation of strain under pure shear. So I'm writing here. So this is the tau square divided by 2g into volume. Or got the point or not? Right. And next one is we are going to learn how to calculate strain energy under bending. How to calculate strain energy under bending. That is also very simple thing. So we can find the what is the bending stress, the strain energy in bending. I give it to you. Please take care about that one. Right. So here strength is under bending. Strain energy under bending. We can easily find it. So this is the beam we are going to consider, which is simply support beam here. So when it is subjected to bending force here, so here we are going to take, this is the cross section of the beam. This is a small, this is the axis. I'm taking a small elemental area, which is having a length of dx. Length of dx. This is nothing but force. And this is the elemental area. That is nothing but dA. Or we can write small elemental area A, and distance between these two points is nothing but y. So if you apply the bending force here, is writing here a deflection. That is this layer will also deflected from the axis, right? So this is the center of gravity. So here is we are writing here strain G is equal to G du is equal to we can write work done, that is force into displacement. So we are writing here force into displacement. Force is nothing but you can take average force, so half into FB bending force into displacement, that is delta L by how much? L, that is the deformation of the body. Okay, right, that is the displacement of the body, or we can write FB into L also, we can write it now. So here that is we can write it. So FB is equal to, according to the bending equation, we can write M by I is equal to sigma B by Y is equal to how much? E by R. Then from this equation, so from this equation, I'm writing sigma B is equal to M by I into how much? Y, I can write it. So what is sigma B? Sigma B is nothing but F by A. So F by A is equal to M by I into how much? Y here. That implies F is equal to M by I into Y into how much? A here. But this is a small force, so I am writing here. So dF is equal to dm divided by I into Y into small area dA. If you integrate it, then we are getting the required value. Or got my point or not? Or you got it? Right. So here, what is the displacement here? D square y by dx square is equal to how much? M by. So EI, that is the formula, we can write it here. So that is the displacement value, d square y by dx square. If you integrate one time, we can get the deflection. That is, we can write integrated, we can write here 1 equation. Another we can differentiate two times. Then we can write here m into, so m divided by ei into x into dx. So we can write here m into into I into x square by 2 into dx also we can write it. So that is the formula we can write it. So if we want to find the slope and deflection, we can double integrate it, then we can get the required value of m. So here also we can, with the displacement, displacement is nothing but we can write m into that value. Okay, so we can get the formula for bending. So integral of, that is we can write m square by 2 times of ei into x into dx. So that is the formula of strain G under bending. So this is the formula. So x is nothing but length of the beam. So m square is nothing but bending moment. So divided by 2 times of E into y into x into dx. So this is the formula of bending strain energy in the material. So otherwise we can write directly also. So if you integrate on both sides, that is strain in a small element, that is nothing but du. If you integrate on both sides, then we can get like this, m square by 2i. So that is force is the average. Force is the average. Displacement is nothing but delta. So delta is nothing but we can write integrate two times here. So then we can get a m into x square something we can get. We can write like this also. Otherwise, we can solve. We can derive this equation another way also. But derivation is not important for you. But the formula you have to remember. So please take care about the formula. That is integral of m square by 2ei into x into dx is the formula for stage for bending. So here I am writing here strain energy under gradually applied load is nothing but sigma square by 2e into volume, and suddenly apply load is nothing but a sigma square by E into volume, and impact load is nothing but we can write in square of that is 2 times of P by A times of P by A if delta L is that is the distance between this is delta is 0, that is H value is 0, that is delta L is minimum, delta L is minimum, that is we are getting this value. So, and we are writing here strain G under P torsion is equal to 2 square divided by 4 times of G. And in case of pure shear is equal to 2 square by 2G into how much volume. In case of bending, you can write the integral of m square into x into dx divided by 2 times of E into y. So this is the formula of strain energy under bending. You get my point or not? So these are the formula we have to remember. So to solve any problem in strain energy. And one more point is also there, that is stage in one dimensional, two dimensional, three dimensional, how to calculate. So here, uh, if I take this one is nothing but a component which is subjected to one dimensional state of stress. One dimensional state of stress. One dimensional state of stress. So this is nothing but a sigma x. This is also sigma x. Then we can write here ux is equal to sigma x square divided by 2 times of E into how much volume. So in case of two-dimensional state of stress, in case of two-dimensional state of stress, I'm taking here is sigma x, here is sigma y. Then I'm writing u total strain energy is equal to ux plus uy. Ux plus uy. Then I am writing ux is nothing but sigma x square by 2e into volume plus sigma y square divided by 2e into volume. So volumes and both are same. So v by 2e is common. Then we are right here sigma x square plus how much? Sigma y square. Oh, you got it? So, but here, what is sigma x? What is sigma y here? So, I'm writing this equation like this. So, volume divided by 2e into sigma x into sigma x plus sigma y into sigma y. But according to your Rook's law, when the component is subject to two-dimensional state of stress, so we can write here sigma x is equal to E into actually epsilon x, and epsilon x is equal to sigma x into E into epsilon x. We can write it here automatically. We can write like this. So I'm writing like this. So see this one. In place of sigma x, I'm writing V divided by 2E into sigma x into E into epsilon x plus sigma y into E into epsilon y. Then I am writing this formula. Then I am writing this formula is like this. So listen carefully. So I'm going to write it here. Strain energy is equal to, so E into E is common. So here is E, both are cancelled. So we can write here V by 2. So V by 2 into sigma x into epsilon x plus sigma y into epsilon y. But in case of two-dimensional state of stress, we are getting sigma x into epsilon x is nothing but sigma x by E minus Poisson ratio into sigma y by E plus in two-dimensional state of stress plus sigma y into sigma y by E minus Poisson ratio into sigma x by E. Or you got it or not? This is for I'm saying two-dimensional state of stress. So please listen carefully here. So here I'm writing B by 2 into, so here we can write here sigma x square by E minus epsilon into sigma x into sigma y by E plus sigma y square by E minus Poisson ratio into sigma x into y by E. Or you got my point or not? So here I am writing V by 2 times of E is common. So you can write sigma x square plus sigma y square minus 2 times of nu into sigma x into sigma y is the formula of strain energy in a two-dimensional state of stress. In a two-dimensional state of stress. Or you got the point or not? Or you got the point? Right. As same as I want to give it to you. What is the strain energy? What is the strain energy in three-dimensional state of stress? I'll give it directly. How to calculate what is the strain energy value in three-dimensional state of stress. After that, I'll give the problems on the strain energy, how to calculate. Right. Strain energy in three-dimensional. Strain energy in three-dimensional. So this is the component I am taking here. So which is subjected to three-dimensional state of stress. A sigma x, sigma y, sigma z. Okay. So what is the total strain energy? We know the total strain energy is equal to how much? Total strain energy is equal to how much? U is equal to ux plus uy plus uz. This is nothing but sigma x squared by 2e into v plus sigma y squared by 2e into v plus sigma z squared by 2e into v. So in all terms, v by 2e is common. Then we can write sigma x square plus y square plus sigma z square. Okay, right. Now here I am writing v divided by 2 times of e into sigma x into e into epsilon x plus sigma y into e into epsilon y. sigma z into E into epsilon z. So the numerator and the denominator of both E is cancelled. Then we are writing V by 2 and sigma x, I can write it here, sigma x by E minus Poisson ratio into sigma y by E minus so Poisson ratio into sigma z by E, this one plus sigma y into sigma y by E minus Poisson ratio into sigma z by E minus Poisson ratio into sigma x by E plus sigma z into sigma z into that is sigma z by E minus Poisson ratio into sigma x by E minus Poisson ratio sigma y by E, bracket close. Now from this one, I am writing, so V by 2E is, 2E is common. Then I am writing directly sigma x square plus sigma y square plus sigma z square plus minus 2 times of nu into sigma x into sigma y minus 2 times of nu into sigma y into sigma z, 2 times of nu into sigma z into sigma x. So this is the formula of strain energy in three-dimensional state of stress. You got my point or not? So this is the strain energy in two-dimensional state of stress. Three-dimensional state of stress. So these are the formulas and this is the analysis of our strain energy. Now I'm going to give some problems on strain energy. After that, I will start with a new chapter that is nothing but springs. After completion of the springs, I will start with deflection of beams. After deflection of beams, I will explain about the uh, series of failures and shear centers. Okay, all right. All right. Now we are doing some problems here now. The question number one on strain energy. So listen carefully. Here is a steel bar of 15 mm in diameter, a steel bar of 15 mm in diameter, that is phi is 15 mm is given. Pulled axially by a force of 10 kilonewtons. I can apply a pull of 10 kilonewtons like this. So the length of the bar is also is given, that is 250 mm is given. Calculate the strain energy stored per unit volume of the bar. So I am writing here strain energy per unit volume. We are going to calculate. So this is the case is given. So Young modulus is also is given. This is a steel bar that is 2 into 10 to the power of 5 Newton per mm square. So how to calculate here now? How to calculate here? So here, first of all, you have to identify which case it is. I have told you number of cases. So which case it is? This is the first case, axial load. It is gradual apply load or static load, whatever it is. It's gradual apply load. So I'm writing here. So strain is equal to sigma square divided by 2 times of E into how much? Volume. Okay. All right. What is the P value here? What is the stress value? Stress is equal to how much? P by A. What is the load is given? 10 kilonewtons. 10 kilonewtons. So into 1000, that is in terms of newtons. Area nothing but pi by 4 into 15 square. 15 square. Then I am getting the value of 176.71 mm square. Or got my point? What is the volume here? What is the volume? Volume is nothing but area into length. Or got my point or not? So I am writing here. Volume we can calculate. Area is equal to volume is nothing but area into length. Volume is nothing but area into length. But he is asking unit volume per unit volume. Actually, we are taking here this volume per unit volume. Unit volume means volume both are cancelled. Directly we can write sigma square by 2 is the formula for strain energy. So then what is sigma here? 176.71 whole square divided by 2 into 10 to the power of 5 value. Or got my point or not? So that is the value. So I got it the value of 8.006 into 10 power of minus 3 Newton per mm cube. That is Newton per mm cube. Right. So for example, if you want to calculate the total strain energy, that is multiplied by area and TL. This is for unit volume. Now we are going to calculate for total volume. It is multiplied by area and TL. Then we can get the what is the total strain energy stored within the material. Okay. So this is the first way of calculation of strain energy. Right. Next one. I want to give it to you. A steel rod of question number 2. A steel rod of diameter 50 mm. So length is also is given, that is 3 meters. So we can write 3 into 1000. Then we are getting in terms of mm. Okay. Find the maximum instantaneous stress induced when a pull of 100 newtons is given. So P is equal to 100 newtons. Kilonewtons is given. Is suddenly applied. Suddenly applied. Find the instantaneous elongation also. So here is we are going to find the stress value. We are going to find the elongation value. So how to find these two values? So take E value is equal to 2 into 10 to the power of 5 Newton per mm square. So this is a common for steel, that is n modulus. Now how to calculate here now? So this is the stress in case of suddenly applied load is always 2 times of gradually applied load. So that is always 2 times of gradually applied load. Or got the point or not? So what is value here? 2 into what is P by A? P by A is nothing but 100 into 1000 divided by area is nothing but pi by 4 into 50 whole square. Then I am getting the value of maximum stress is nothing but 101.86 Newton per mm square. Then how to calculate the elongation here? So delta L is equal to how much? According to this one, PL by AE. PL by AE. What is P by A stress? So we can write sigma into L divided by E. What is sigma? 101.86 into length is nothing but 3000 mm divided by E is nothing but 2 into 10 to the power of 5. Automatically we can get 1.528 mm is the elongation of the bar due to the application of the 10 kilonewton meter. I got the point or not? So why I am going to apply this one now? So for gradual apply load, in case of gradual apply load here, that is sigma square by 2e into so volume. That is the value. So suddenly apply load is equal to this is the P by A. Or you got my point or not? That is two times we are getting that value. Suddenly apply load is nothing but two times. That is sigma square by suddenly is nothing but sigma square by E. There is no two here. Then we can write here uh, S is equal to two times of UG. That's why I'm writing this value and substitute. Automatically we are getting the required value of this one. Okay, right. This is the one type of on the strain edge. These two problems are belongs to gradually applied load and suddenly applied load. When the suddenly applied load is given, then that is always two times of the gradually applied load. So be careful about the things. Now I'm going to give one more problem here. That is two elastic bars of same material and length. So here is one bar is given. This is another question. I'm going to give it to you. This is one bar. This is another bar. Two elastic bars of same material. Material, material same. Material same. And length. One is circular section. This is in circular section of diameter 100 mm. Of diameter is given 100 mm. Got it? Another one is square section. This is the square section with a side of 100 mm here. Please. Right. Sorry for the disturbance. So this is the material which is having a square section of side is equal to 100 mm into 100 mm. So observed same amount of strain energy. So this is strain energy in the bar 1 is U1. The strain energy bar 1, 2 is nothing but the given is nothing but U1 is equal to how much? U2. By the axial force. This axial force and axial force are same also. Then find the ratio of the stresses in the bars. So here is we are writing sigma 1. Here is I am writing sigma 2. They are asking ratio between sigma 1 divided by sigma 2, how much it is. Okay. Right here I'm going to write it. So this is also uniaxial state of stress. So it is axial load. So it is gradual applied load. So that is U1 is equal to how much? Solution I'm writing here. U1 is equal to U2. U1 is nothing but sigma 1 square by how much? 2E into volume is nothing but area into length. Sigma square by 2E into area into L. So when both are made of same material, 2E cancel. Both are having same length. And here I am writing here sigma 1 square by sigma 2 square. So I am writing here sigma 1 square divided by sigma 2 square is equal, here is A1, here is A2. That is A2 divided by how much? A1. So I'm writing here sigma 1 divided by sigma 2 is equal to square root of A2 by A1. So what is the A2 value? A2 value is nothing but 100 into 100. That is the area. That is pi by 4 into how much? 100 square. So these two are cancelled. Then we are getting the ratio is approximately, that is a sigma 1 by sigma 2. I got it, the 1.128 is the ratio. That is the ratio of stresses. So they will ask any type of question by comparing the strains in suddenly applied load or gradual applied load. They will give the comparison. So in which case we are getting the more stress in the material under gradual applied load or suddenly applied load or impact load. They will ask any type of questions. So please take care about those points, right? Right. So now I'm going to give another one. So how to solve it? Okay, right. Okay, so this is another problem. So a uniform weight falls by 30 mm on a collar rigidly attached. So this is the problem is given. So this is the collar. So this is the weight, which is 30 mm distance from the bottom end. That is 30 mm height, which is given. Falls at a distance of 30 mm so to a rigidly rigid collar attached to the lower end of the vertical bar, 4 meters long. So the bar is having a length of 4 meters. So here is I am writing. The length is equal to 4 meters here. And area of cross section is given. So that is 1000 mm square. 1000 mm square. The maximum instantaneous extension is found to be 3.66. Extension is found to be, that is delta L is given, so 3.66 mm is given. So take E is equal to, this is 2 into 10 to the power of 5 Newton per meter square. So it is a steel bar. So what is the question he is asking now? So he is asking if the maximum instantaneous tension is found to be 3.66 mm. Find the corresponding stress and the value of unknown weight. You have to find the stress value and the corresponding weight value we have to find it. That is nothing but load we have to find it. Or you got my point or not? So how much load we are going to release it here. But this load is released at a distance of how much? 30 mm. Okay. So this is the problem which is given like this. So I want to give the solution for this. Please listen carefully here now. So here we know that this is the case of impact load. So in the case of impact load, we are writing here a sigma square by 2 times of E into volume is equal to how much we are getting here. So P into H plus delta L. H plus delta L. So here is sigma square divided by 2 into A is nothing but 2 into 10 power of 5 into area. Area is nothing but 1000. So into L is nothing but 4 into 1000 is equal to P into. So P into how much H value, that is 30 mm, plus delta L is nothing but 3.66 mm. So you have to find the P value. First of all, you have to find the stress value here. You have to find the stress value here. Maximum stress is equal to how much? So I am writing here maximum stress is equal to, so E into maximum strain. E into maximum strain. You are writing E into strain value. Or you got my point or not? What is the strain here? Strain is nothing but delta L by L. So we know the delta L by L. So E is equal to delta L divided by L. Delta L is nothing but E is 2 into 10 to the power of 5. Delta L is 3.66. Length is 4 into 1000. Then we are getting the stress value. I got it 183. That is 183 Newton per mm square. I got it. 183 Newton per mm square. Then I'm going to substitute here. Then I will get the value of P here. Then I will get the value of P here. How to find the P value? So here I am writing here 183 square divided by 2 times of 2 into 10 power of 5 is equal to into volume. Volume is nothing but 1000 into 4000. So is equal to P into, so 33.66. So then what is the value of P here? P is equal to 9949.2 newtons. So this is the value of load which is released at a distance of 30 mm from the bottom end of the bar, which is connected to a rigid collar. Or you got your point or not? Alright. So this is the one way of solving the strain energy problem. So I want to give one more problem on this one. So please try to listen carefully. So this is the diagram is given. So for the strain energy problem. So this is the bar which is fixed at one end. So other end is This is a rigid collar. So this is the block which is sliding over this bar. This bar is a cylindrical bar. So this bar is having a weight of 300 newtons. This diameter of the bar is 5 is equal to 45 mm. 45 mm. It will move with an acceleration of velocity of that is 2.5 meters per second. The block slides on the bar, that is a cylindrical rod bar of diameter 45 mm. This is the block which is sliding like this, but it is moving with a velocity of 3.25 meters per second and goes to impact the rigid collar. If the block is moving with a velocity of 2.5 meters per second, so the length of the bar is also is given. The length of the bar is also is given. That is nothing but 1500 mm. If the block is moving with a velocity of 2.5 meters per second and goes to impact the rigid collar, then find the stress induced in the bar. Take E is equal to 2 into 10 power of 5 Newton per mm square. Or you got the point or not? What I am saying here, a block of weight 300 newtons is sliding and at the same time it is moving with a velocity of 2.5 meters per second and goes to impact the rigid collar and goes to impact the rigid collar. Then find the what is the stress induced in the bar after impact of the rigid collar by this moving weight. So all the data is given, in the modulus is also is given, all the data is given. Then how to find this stress in this bar? Stress in this bar, I want to find it. So when this weight is goes to impact this bar automatically will deform deform like this. It will bend like this or it will deform like this. During the deformation, it stores some energy. Uh, That stored energy is nothing but strain energy. So before going to impact this rigid collar, which type of energy contained by this block here? So kinetic energy. The kinetic energy of the block is equal to half into m into v square. This is the energy of the block before going to impact the collar. So if this kinetic energy of the block goes to impact this rigid collar and it is converted into strain energy stored in the bar, strain energy stored in the bar. That is nothing but after impact. This is nothing but it is a third case, that is impact load. That is sigma square by 2e into how much? Volume. How much here? Into volume. Or got my point or not? So what is the kinetic energy of the block here? So weight is always equal to m into g. So mass is equal to how much? Weight by g. So weight is given. Acceleration is nothing but all of 9.81. So then substitute here. So this is equation number one, equation number two. After impact, I'm going to equate. So one is equal to how much? Two after impact. Then I'm writing here half into W by G into V square is equal to sigma square by 2E into volume is nothing but area into length. So here I'm going to find the sigma value. Then I'm writing here half into 300 divided by G is 9.81 into V square, that is 2.5 meters per second. So take care about those values here. Is equal to sigma square divided by 2e into area is nothing but in case of mm square we are getting here into length is in terms of meters. So we can write here area and length. Then sigma is equal to, I got it approximately, that is 114.144.33 Newton per mm square. I got it. So please take care about the units also. So this is the way of calculation of strain energy. I got my point or not? Or you got it? Right. So I want to give one more question to you. So please take care about that one also. This is also very easy question, but I have to take care about the what is the conditions are given in this problem. Okay, right. So this is the next question on. So this is the bar is given, which is a uniform cross section of the bar of diameter is D, which is subject to a load of P here. A load of P here. And here another bar which is having different types of area of diameters at different points, but having this length is equal to how much L here. And this is also subject to same tensile force of P. And this length is nothing but L by 2. This is L by 2. And this is nothing but D. And this is nothing but D by 2. So this one, both are same. Right. So these are the two diagrams are given. So the question is given the two bars of same length and material subjected to the same axial tensile load. Both are same material, so both are subject to same tensile axial load. The first bar is of uniform cross section for diameter d, and the second bar is diameter d for the first half of its length. Uh, the second bar is having diameter d up to first half of its diameter, first half of its length, and diameter d by 2 for the remaining length. Compare the strain energy stored by the two bars. So compare the strain energy. So here is I'm writing U1, here is writing U2. So I'm writing comparison U1 by U2. We are going to take it. So that is nothing but to find the ratio between U1 by U2. Or you got my point or not? Right. So how to find this value? Right. I'll give it to you. So listen carefully. So here U1 by U2. So U1 by U2 is equal to, here is sigma 1 square divided by 2E into how much? Volume divided by sigma 2 square divided by 2E into how much? Volume here. I got my point or not? I got my point? Right. Here is first of all U1 I'm going to find it. So U1 is nothing but strain energy, that is P by A. So I'm writing here P by A whole square into 2E into volume. Volume is nothing but uh, pi by 4 into how much d square into L. That is the value. And U2 is equal to U2 is equal to how much? This one is nothing but a half of this portion. So strain energy in this portion plus strain energy in this portion. So this portion is nothing but capital D. This portion is nothing but small d. Then we can write here. So P by A. So P by on this portion. So P by A is nothing but P by pi by 4 into how much? Capital D square. That is whole square divided by 2 times of E into area pi by 4 into D square into L by 2 plus, and this strain energy, that is P divided by pi by 4 into D by 2 whole square and square divided by 2E into pi by 4 into d by 2 all square into L by 2. So after dividing these two, we are getting the ratio of, so U1 by ratio of energy stored by the two bars is equal to U1 by U2 is equal to 2 by 5. So this is the ratio we are getting. So in all cases, divide these two, then take the common terms and multiply those things. Automatically, we can get the required value. Okay, I got it that value of 2 by 5 ratio, 2 is to 5 is the ratio. Right, so this is the way of solving this energy problem. So first of all, we have to identify which case is given. So depending on this case, we are going to solve the problem. So the problem is given on torsion or shear or gradually apply load or suddenly apply load or impact load. So we can easily solve it. Right, so this is about this energy. Now here I'm going to give it to you. So that is nothing but next chapter. That is chapter name is springs. This is also very, very important chapter. So springs in mechanical point of view and civil point of view also, but especially in mechanical point of view, it is very, very important. So what is the definition of spring? First of all, I'm going to give the definition. What is the uh, definition of spring here? So I'm writing here, spring. It is a mechanical device. It is a mechanical device which stores energy after application of applied force. It is a mechanical device which stores energy after application of the applied force. So it can also stores the energy. So it is also having strain energy. So when the spring is compressed or tension, it is also having strain energy. We can find when the member is said to be under tension or compression, we know that what is the formula for strain energy. That is sigma square by 2E into volume. Then we can apply, then we can find the what is the strain energy under axial load in the springs here. So here there are different types of springs are there. So spring is a mechanical device which absorbs energy during the compression, and it also gives the energy during the relieving of the load. And here these springs are different types here. So types of springs I'm writing simply types of springs. Types of springs here. So springs are different types. First one is nothing but helical springs. Next one is spiral springs. And next one is leaf springs. So these are the types of springs here. So helical springs, spiral springs. Helical springs are like this. So I don't know if you know it. And spiral springs are like this. And the leaf springs are like this. I don't know if you know very well. These are nothing but leaf springs. So here, most of the cases, for most of the cases, we are using the helical springs, but especially for heavy loads, we are using leaf springs. So heavy loads means in case of four-wheeler, six-wheeler, eight-wheeler, and 10-wheeler, 20-wheeler, so which carries heavy loads. So we are going to use leaf springs also. And spiral springs we can use in toys, so to operate the toys also. So these are the types of springs here. So here we are going to discuss about the helical springs. So that some points are very, very important. So here, if you take this is the helical spring example. If you take this is the load which is acting at the free end of the spring. So if you draw a tangent here, if you draw a tangent here, so this tangent always makes an angle of alpha with the horizontal here. That angle is always named as helix angle. This alpha is named as helix angle. When alpha is greater than 10, it is named as open coil spring. Open coil. Alpha is less than 10, it is named as closed coil. So here there are different types of helical springs. One is said to be uh, open coil helical spring, one is said to be closed coil helical spring, depending on the helix angle. So alpha is greater than 10 degrees and it is less than 10 degrees. Then we are getting two types of coils here, that is open coil and closed coil here. So here also we are going to find one thing here, that is what is the deflection of the spring and what is the stiffness of the spring. So here we are going to calculate 2 points. If you attach the load at the free end of the spring undergoes some deflection or deformation. I want to find the what is the deformation or displacement or deflection of the spring by the application of external load, which is acts axially or parallel to the surface. So there are different types of forces: tensile force, compressive force, and shear force, that is torque. Uh, there are different types of forces we can apply on this spring also. But here there are two types of springs we are using here. One is tension spring and one is compression spring. So both carries axial load. I got my point or not? So when the spring is carries axial load, then we are going to calculate what is the value of delta. Delta is nothing but deflection of the spring. After know the deflection, we are going to find the what is the value of after deflection. Automatically, we are going to find stiffness of the spring. So first of all, I'm going to define the stiffness of the spring here. So what is the stiffness here? What is the stiffness? Stiffness of the spring here. That is always indicated by the symbol K. I got my point or not? So I want to define the spring stiffness here. So it is a spring which is said to be a helical spring, which is attached a small weight at the bottom. So this weight is W. Then it will undergo some displacement up to this one. So the displacement is nothing but delta due to this load. What is the stiffness here? Stiffness is always different load per unit deflection. Load per, I'm writing here, load per unit deflection. Unit deflection. Load is nothing but W and deflection is nothing but delta. So that is the formula of stiffness. Units is nothing but Newton per mm. Newton per mm is the units of stiffness. So I already told you in torsion offsets. So we know that what is the value of torsional stiffness. I have already told you. So here is also we are going to learn first of all what is the deflection of the spring and what is the torsion of the spring. That is, what is the stiffness of the spring we are going to calculate. So here I'm going to explain when a helical spring is subject to axial load, what are the relations we are going to get it. So how to find its deflection and how to find its stiffness. When a helical spring is subjected to, so I'm writing here. So listen carefully. Spring, that is helical spring, is subjected to axial load. Helical spring is subject to axial load. So listen carefully. I'm going to give the diagram also. This is the Right. So here we are going to add the weight. Here we are going to add the weight here. So this is the, so here is I'm going to, right. So this is the radius of the coil. This one is nothing but radius of the coil, mean radius. It also is equal to mean diameter. That is 2r. So radius is nothing but r here. So if you take this is the cross section, if you cut it, it is always appeared as a circular form, which is having diameter of capital D. So this is nothing but is equal to capital D. Capital D is nothing but diameter of the coil. Small d is nothing but diameter of the spring wire. Or you got my point or not? Okay. Right. So here I want to find it first of all. When this axial load is acting at the free end of the spring here, then what happens here? So there must be a energy due to axial load. So first of all, I'm going to write it here. Strain energy due to axial load is equal to how much? Half into W into this deflection. This deflection, I'm going to write it delta. So that is the strain energy due to axial load. This load is nothing but W I'm writing here. So please take care about that. Okay, right. So when this load is acting in this direction, at the same time, it is also twisted here. Twisted here. When you apply the load in downward direction axially, at the same time, these coils are twisted like this. So there must be a strain energy due to twisting also. So I'm writing here strain energy due to twisting. That is half into T into how much? Theta. Half into T into how much? Theta. Or you got my point or not? Or you got my point? So here, how much strain energy during the axial direction must be is equal to strain energy under twisting. So both are same. This is equation number 1 and this is equation number 2. So I'm equating 1 and 2. Equating 1 and 2. Equating 1 and 2. Then if equating 1 and 2, then I'm writing half into W into delta is equal to half into T into how much? Theta. Then half of both are cancelled. What is torque here? W into delta is equal to torque is nothing but force into displacement. What is the displacement here? Force into radius. That is R into theta here. R into theta here. Force is nothing but W. So I'm writing here W into delta is equal to W into R into theta. Or got my point or not? What is theta? Theta is nothing but from this equation. T by J is equal to tau by R is equal to G theta by L. So theta is equal to so T into L divided by J into G. So I'm going to write it here W into R into T into L divided by J into G. That is W into R into what is T value? T value is again F into R. F is nothing but W into R into L divided by J into G value. Are you got it? Now I'm writing here. So W into delta is equal to here is W both are cancelled. One W cancel. Then I'm writing delta is equal to so W into R square into L divided by J into G. That is the value you got it. Now I'm going to rewrite this equation. So listen carefully here. So delta is equal to W into R square into L divided by J value is nothing but pi by 6. J value is pi by 32 into small d power 4 into G. Now what is L here? L is nothing but length of the coil, length of one coil. L is equal to length of one coil. That is also is equal to 2 pi R is for length of one coil. So this is the length of one coil. So this is a perimeter. So here we are having number of coils. So into N. That is N is nothing but the number of coils. N is nothing but the number of coils. Now here I'm going to write it here. Delta is equal to 32 times of W into R square into 2 pi R into N divided by pi into d power 4 into G. Pi both are cancelled. 32 fours are 64 here. So I'm writing 64 times of W into R power 3 into N divided by G into d power 4. Find the value. So that is the value of G or delta value. So delta is equal to 64 times of W into R power 3 into N by G into small d power 4. This is the value of deflection of the spring due to axial force. Due to axial force. Or you got my point or not? Right? Now I want to find the stiffness value here. Now I want to find the stiffness value. What is the stiffness value here? Stiffness K is equal to W by delta. W by delta. So W divided by 64 times of W into R power 3 into N G into D power 4 G into D power 4. Then here, so W both are K. Then I'm writing here K is equal to G into D power 4 divided by 64 times of R power 3 into how much N is the value of stiffness of the spring. So these are the two equations we can use to calculate what is the stiffness of the spring and what is the deflection of the springs here. So after finding that, so we can apply this formula to calculate any value in springs. We can calculate load required and the number of coils are required and what the radius of the coil is required and what is the diameter of the spring wire is required, right? K is equal to W by delta. So we can find any one here now. So now I'm going to give it to you when springs are connected in series and parallel. So what is the value we are getting? So what are the values we are going to getting it? So these are the two formulas we have to remember it. So after that, here springs are contains series and parallel. Springs are in series and parallel. So these are the two formula we can remember. That is, I'm writing here delta is equal to 64 times of W into R power 3 into N divided by D power G into D power 4 and K is equal to G into D power 4 by 64 times of R power 3 into N. So these are the two formulas we can remember. Then I'm going to apply these two formulas for springs are connected in series and parallel. When two springs are connected in series here, so this is a series case. This is one spring and this is also one spring. And this is connected to a small weight W here. The stiffness is nothing but K1, the stiffness is K2, so deflection is delta 1, deflection is delta 2. When two springs are connected in a series, when two springs are connected in series, then what is the total deflection? Total deflection is equal to how much? Delta L1 plus how much? Delta L2. So delta L1 plus delta L2. And what is the total load here? Total load is equal to how much? W1 plus W2. This deflection is also same. So what is the total load? Load taken by this one and this one here. So W is equal to how much? W1 plus W2. So both loads are same. The spring one is constant when the springs are connected in series. Then deflection of the spring plus deflection of the spring both are not same. So both are having different types of spring constants. That is stiffness of the springs. So if you apply the load at the bottom, so what is the load taken by the spring one and load taken by the spring two? So we are going to write that. So here is also we are taking this. This is a spring one. So this is a spring two. Both are connected in parallel. So we are going to put weight here. That is W. This is K1 and this is K2. This is delta 1 and this is delta 2. Here, delta is equal to delta L1 plus delta 2. W is equal to W1 is equal to W2. That is load on this one both are same. And next one is here is delta L1 is equal to delta L2 is equal to delta. So del W is equal to W1 plus how much W2. Load taken by each bar is each spring is not same. Here is load acting on each spring is same here. So these are the formula we can use it here. So if you write this one is constant, so spring constant here. In the case of this one, when connected in parallel, so I can write like this. So delta is equal to uh, W by K is equal to how much? W by delta, but delta is equal to W by K is equal to W1 by K1 plus W2 by K2. But W1, W2 all are same. Then we can get 1 by K is equal to 1 by K1 plus how much? 1 by K2. So this is the formula we can use to calculate. So equivalent stiffness of the spring when springs are connected in series. And at the same time, so here I'm writing here delta W is equal, W is nothing but from this equation. So K into delta is equal to K1 into delta 1 plus K2 into delta 2. So here is delta 1, delta 2 all are same. K is equal to K1 plus K2. So this is nothing but equivalent stiffness of the spring when two springs are connected in two springs are connected in parallel. Or got my point or not? So when springs are connected in series, we can use this formula also. So K equivalent is equal to, we can write here K1 into K2 divided by, so K1 plus K2. So this is the equivalent stiffness of the spring. This is the equivalent stiffness of the spring when the spring is connected in series and parallel. So in this way, we can calculate stiffness and uh, deflection of the spring by the application of the Excel. Uh, నానా నానా అవలేదు నానా Uh, okay, so this is the way of calculation of all these values. So remaining we will discuss in next class. So please take care about up to this one. So in the next class, I will give the explanation about some problems on springs and I will give the explanation about the deflection of beams also. Okay, thank you very much to all of you. Thank you very much. We will meet in the next class.